Welcome back, and we're moving on. We're continuing our discussion of data models, and we'll devote more attention to relational data models, and we will also discuss entity-related diagrams, what these are and why we need them in the context of data models. So let's see. So in this class, we'll work with relational database models using Microsoft Access software. Microsoft Access is among the more commonly used programs for that purpose, and it's good enough for personal use and even small applications, and this is why it's widely utilized in government agencies and nonprofits, and particularly in smaller government agencies. So it's not as costly as software that would be required for much larger databases, and it's much more accessible and easier to use. So it can handle few users, and it follows the necessary industry standards. So, but there are more complicated software applications, obviously, used to work with larger relational databases, and such databases may have many simultaneous users, many more, but they require more advanced software like Oracle, MS SQL Server, and so on. So there are other interesting models you may have heard before. Well, you have heard before, like linked data that I mentioned briefly, or dimensional models, which we're not going to be able to cover in this class, and we're not going to be going into details about this. But if you are interested in learning more about this, College of Engineering and Applied Science offers good courses in this area. So check out the Department of Computer Sciences and Information Sciences. So the first step in learning about relational models is to be familiar with. We need to be familiar with the basic terms used in this context. So this is a bit theoretical, and it will be easier to connect some, attach some meaning to these words as we work with specific data sets. But I still wanted to give you kind of a preview. So an entity, key term that we hear, it's something of importance that to the use that is being tracked. So it could be a specific topic we're interested in, or a student, a faculty member, type of furniture in the building. So all of these can be our entity, our main focus. So the data, the information about this entity, are captured in a relation, which is basically a table. So the rows in the table are called tuples in a database context. So each tuple is a horizontal row providing different information about our entities. This information are attributes. So each column contains information on different attributes. Is provided in separate vertical columns. They're also called variables. So each column contains different type of information. It could be text, number, etc. So for instance, each row is different student, right? There is student 1, student 2, student 3, say at least 5 students from PED 504. So that's one column. The next column is average GPA for student 1, for student 2, for student 3, and through 5. The next column is age. The next column is date of birth. So the first column where we have students, that's our main entity. And the next columns, age, GPA, date of birth, these are variables or attributes or columns. All of these different synonyms are used for that purpose. So in these columns, we can have age, we can have text, we can have any kind of entry basically. So, and all of this is organized obviously in a table, or in this context, it's a bit confusing, but table is a relation. So this table has rows, a tuple, columns, or attributes. So each attribute will capture different information related to our entity. Our entity in the example that I just mentioned is a student, and each attribute will capture different information about the student, date of birth, GPA, age, etc. So these are the basic terms. It may be confusing, but if you remember a couple of these, it will be great. So in every table, we want to have an identifier for each member of that table. So we call these identifiers keys or a key. So usually there is a column that contains all unique keys. An example of a key would be your student ID or net login or social security number. So every single one of you will have some kind of unique identifier, so that there are no two students with the same social security number and we don't know who is who. So all of these alternative keys are all candidate keys. They all can serve as a good, unique identifier. All these alternative keys that I just mentioned, they can be unique identifiers. As long as this attribute is unique to each student, we can use it as an identifier. It's a candidate for an identifier. A date of birth is not, because it is likely that the more people we get in class, the more likely there are going to be at least two people who have the same date of birth. So there is a column with all different social security numbers, and if we search for your social security number, we find the row where all your data is. But we may have two different tables or different relations. In one of these, we have your performance, and the other, we have your background. So there are two tables, one on your performance, separate table, one on your background. And in each of these tables, there is a column with a unique identifier. So we can use this key, right? We can find social security number in your performance table, and we can find your social security number in your background table. So we can use it to relate one table to another, or to merge them so that all data are in one table. If we didn't have any unique identifier or unique key, we would simply have to have, we would have basically grades listed without knowing whose grades they are. So I hope you understand the importance of a unique identifier. And this unique identifier will show up in several tables and will help to connect these tables to one another. So here is a simple example of what I was just talking about. So it's a table with student information. It's much easier to see than trying to imagine it. So going back to what we just discussed in the previous slides, the entity in this case is students in an organization. So we have a collection of students from a specific organization. And the primary key, as you can see here, is the social security number. It's a unique identifier. Each student has a unique ID. And tuples are the rows. So for Sarah Smith, we have several attributes provided here: occupation, date of birth, and social security, first name, last name. So all of these are attributes. Each separate attribute is stored in a separate column, as we can see here. These columns are also called variables. So in a way, column, variable, attribute are referring to the same thing here, if we're less specific here. So if you look at it carefully, what we use as a primary key is social security number. We know it's unique, but we could have also used a combination of first name and last name. You can combine these two attributes and have Jim Parker, with underscore between these two words in one column. So that could be our unique identifier, but would it be as reliable as the social security number? Most likely not, because I could bet money that there are quite a few Sarah Smith in the United States and Jim Parkers. So once in a while, you can get a you could get a duplicate. The date of birth, of course, if you combine first name, last name, and date of birth into one as a unique identifier, that's going to be even harder, but still, I think with 330 million in the United States, 330 million population in the United States, there is going to be some duplicates still. So that's an example of a relation or one table. It's only one table here. But what characteristics actually make a table a relation? We I can imagine you've seen a lot of tables in Excel, or organized in one way or another, but are all of them a relation, as as we use the term in this context? So are these always the same, in other words? But in short, no, because rows in a relation must contain data about an entity. We have our major entity, a student, and rows will contain different information about our entity. And columns, the vertical ones, contain data about attributes of the entity. So each column contains information on specific attribute of the student. Each column is either about performance or, say, GPA, date of birth, and so on. So then, as a result, each cell of the table holds a single value. Can't combine date of birth with social security number into one cell. So, and it's basically, if there is more than one value in a cell, it's a violation, and technically it's not a relation. So all entries in a column are of the same kind, basically. If we have a column for height, there is no entries for weight, for example. So we have unique column names, so they're not confusing, and column order doesn't matter. We can put our unique identifier in the middle, but because we have unique names, we can refer to columns by their names rather than by their order. Say refer to column 1, column 2. We don't do that. We have the name of the column, and if we so basically if we change the order of the columns, it won't affect the utility and meaning of the data. So the same goes for rows. In what order the students are listed, if we go back to our previous examples, doesn't really matter. So because we look by the social security number, wherever it is, and then we look for, say, age for that student. And wherever age is in the first, second, or sixth column, we're going to find it by the column name. And there are no duplicates where two rows contain identical set of values. So as a thought example, try to think to what extent our Sparks hospital discharge data meet all these 8 criteria. Is it really a relation, or is it still just a table that does not meet all these criteria and can be counted as a as a relation? So just as heads up, it's there is really one bigger problem that I see with that data set is if you remember it while watching. So some variables are really identical, but they have different formats. So like there is a numeric versus character variable for disease severity, or the procedure code and description. So how we treat that depends. If they contain basically different information but coded differently, say severity can be coded from 0 to 5 or from mild to extreme. And this is the same information and just different coded different. So this would probably be a problem if we wanted to call that table Sparks dataset a relation. So here's another quick example of data on faculty. So faculty ID attributes. If we change order of columns or rows, it doesn't really matter, and each row contains unique data. So this little table here does meet our criteria for relational data for relation. So thinking about data sets, it often helps actually to represent them with entity relationship diagrams. And such visualizations, if we can represent them with diagrams, help us form a conceptual model of the database. It's another way to communicate and come to an agreement what the database will look like if we're trying to create a new database, and everyone may have a slightly different idea. And if we make a diagram and discuss it, we come to an agreement. And it's important for stakeholders, those who create the database, of course, because then it becomes clearer for them what the task is, what is expected, and those who will use the database. So, and it basically, you think about entity relationship diagram as a blueprint of the data structure, of the structure of our database. And again, to give an example, here's here's one of entity relationship diagram. So each table is represented by one of these rectangles. So faculty and students, we basically have two tables here. So in this database, there are two tables devoted to two different entities. One entity is faculty, the other entity is students. And each entity apparently has its own attributes shown in the bubbles in the diagram, as you can see here. So what we know about faculty: office phone number, name, and faculty ID, department, email, building name, roommate, room number, and so on. Same goes for students. So each of these bubbles becomes a column in our tables, and we have relationship here between tables shown with the row. So two tables, students and faculty, each with their own attributes, and then there is a relationship between them who, well, advising basically. You may have noticed in the diagram that I just showed you that different parts of the diagram are, visualized with different types of notation. So the entity is, a primary piece of information around which everything is organized. Our entity is in a rectangle, and the name of the entity is usually capitalized. Now, there are attributes related to the entity. This where the bubbles go in different directions. The attributes are in these bubbles, and they are usually spelled using one word, proper spelling. And if we have surgical procedure, we cut it to search pros, so that you know what this means, but it's in one word. Now, there are other attributes that were underlined. So this is basically our primary keys that are unique attributes and will be used to identify our records. A unique attribute means that the values of the primary key are unique for all observations in our table. Each student has a unique primary key. Each faculty has a unique primary key. So some attributes, like this one here, so they are called composite attributes. So name is a composite attribute. It has two parts and it can be separated in two columns. So basically it has what's called two atomic pieces that can be divided, can't be divided any further. Address is another composite attribute because can it be divided? Yes, it can be divided into street, street number, apartment number, city, state, zip code, and if you want, country. So this division helps us if we want to filter out observations by the zip code and focus on specific geographic location. So these atomic attributes can be put back together if need be. We can separate first name from last name, or we can put them together with a space between them. So in the diamond, the last piece of the diagram, the last type of notation, shows represents a relationship. So it explains what the relationship is between the entities and in the database. So in our case, that was advising. This is how students were connected to faculty members. So here is a diagram shown along with the actual data. So we have our entity, the main topic of this table, and in our case, it's basically students, and we have different attributes related to our entity. So our attribute A would be the social security number. It's with underlining, and we know that the social security number is our primary identifier. And we also have three different additional attributes: name, date of birth, and occupation. And attribute D here is the name, further divided into two attributes, first name and last name. So this is how a database is related to this entity related diagram as an example. So there is another important characteristic of the relationship called cardinality. We can have one-to-one relationship, one-to-many, or many-to-many. So there are relationships where each element of one entity has a relationship with only one element of another entity. For example, every person has only one social security number, and that's one-to-one relationship. One-to-many example is every person can have several cars, several pens, etc., several items that we will possess. And many-to-many would be how students are related to courses. Many students can be in one course, and each student can be in many courses. As a result, the relationship between two entities, one being courses, the other students, has many-to-many cardinality. As we will see, there are more examples of this in the course of different types of relationships or cardinality. So most of the time in real life, we have one-to-many or many-to-many relationships, and one-to-one is usually very hard to come by. So to go back to our diagram and to say a few more words about cardinality as an example. So in this case, faculty are one entity related to students, obviously another entity. They are in rectangles, so we know these are the main entities that form the basis for the tables, table 1 and table 2, and they're connected with advising. And this notation here and this here means one faculty can be connected through advising to many students, and but only each student can be connected only to one faculty. Otherwise, we would have this notation here, we would have it here, but this means one. So what this basically is, the database, the diagram says, is basically one faculty can be connected to many students, and each student can be connected to only one faculty. Each student, one student cannot be advised by many faculty members, and that's what the diagram says here. So just a detail and something you may come up if you look at other diagrams. But as you can see, this can be very helpful if you're trying to communicate. If someone who develops a database trying to communicate with stakeholders what they want, what they expect, and once we have diagram in place, it becomes much easier to do that. So now we will see how to create diagrams like this in our future videos. Okay, I hope you learned something new. There may be a lot of information. You may need to watch it twice, but again, it's not to be too much stressed about it. Just the general concepts that I hope you will keep in mind as we move along through the course.